Okay, we're going to do some example problems for rotational kinematics. First one here, what is the angular velocity in radians per second of the minute hand of a clock? An oldie but a goodie. The first thing you have to know is what a non-digital clock is. And so I have a clock and it has a minute hand, that's the long hand. This right here says that it's about 10 past 2. And it's the minute hand that goes around the clock, ironically, once an hour. The average, so I'm going to find the angular velocity by using average angular velocity formula and saying it is delta theta divided by delta t. Delta theta, how far does it go in 1 hour? Whoops, I just misspelled theta. Let's try that again. Delta theta is 1 revolution, and I have to convert that into radians. This is a tough one. That is 6.28 radians per revolution, and so it goes around 6.28 radians in 1 hour. However, here's where one place we have to be careful. The direction that it travels is clockwise, and we've already defined the counterclockwise direction as the positive direction. So we're going to do here negative 6.28 radians divided by 3,600 seconds, and that's going to give us an average angular velocity of 1.74, I'm sorry, negative 1.74 times 10 to the minus 3 radians per second as the average angular velocity of the minute hand of a clock. Okay, let's do another one, and it will appear immediately. Okie doke. Take a look at this question. We're given that the equation of motion of a bug on a turntable is theta is a function of time is 0.3t cubed minus 6t plus 4. We're reminded these are all MKS units, which means that the times are in seconds and all the angular quantities are in radians or radians per second squared, etc. Okay, what is the angular velocity of the bug at t equals 2 seconds? This looks like problems we've done before with linear motion, and we attack them exactly the same way. We start off by saying, okay, we want the angular velocity. That means we need to find the function angular velocity as a function of time, and that is the derivative of position, angular position with respect to time, d theta dt. And we do this by the normal method. Let's see, we're going to get 0.9t squared minus 6 for the angular velocity. And at t equals 2 seconds, so omega at 2 would be 0.9 times 2 squared minus 6, which is clearly equal to negative 2.4 radians per second. Okay. So it's going clockwise at 2.4 radians per second. Perfectly reasonable angular velocity for a bug. It shouldn't get too dizzy yet. Letter B says, what's the angular acceleration? And angular acceleration, of course, is the first derivative of angular velocity as a function of time, or the second derivative of angular position, and that is going to be, again, by the normal methods, 1.8t minus nothing if I'm differentiating the angular velocity with respect to time, which means that alpha at the 2 second mark is going to be 1.8 times 2, which is going to be 3.6 positive 3.6 radians per second squared. What can we conclude at this point, given that the angular velocity is negative 2.4 radians per second, the angular acceleration is positive 3.6, and that is that the bug's rotation is slowing and will soon stop and reverse direction. And at some point, the bug's going to fly off the turntable, and we'll feel bad about what we just did to the bug. So let's move on to another example problem, which shall appear almost immediately. Okie doke. So here's a problem that has to do with throwing a frisbee, and I'll give you a chance to read it, and you can pause. So I'm going to start babbling. And it says, just before you throw it, it's motionless in your hand. The instant you lose your hand, it's rotating clockwise at 54 revolutions per minute. I'm going to say something about these numbers. The 54 revolutions per minute I made up. I think that's somewhat reasonable. It would be interesting to film a frisbee with a high-speed camera and see, in fact, how fast it is rotating. The second number here, you get it up to this rate through only 1/2 a rotation during the actual throw. If you Google slow motion frisbee throw, or not, look up some videos on YouTube, or just think about throwing a frisbee, that's actually reasonably accurate. That you actually only rotate the frisbee about 1/2 a rotation during the actual throw, and yet you accelerate it up to that rate, or something like that. So, question A: calculate the average angular acceleration of the frisbee during the throw. All right. Let's consider what we know and what we want to find out. We want to get average angular acceleration, and we are going to assume that during the throw you're accelerating it uniformly. You're making it rotate faster and faster uniformly, which means that we can use the big ugly formulas based on that assumption. Okay, your initial angular velocity is 0 because before you throw it has no angular velocity, and that your final angular velocity at the time that it leaves your hand is 54 revolutions per minute. And let's consider the sign. It's clockwise, so we actually have to say it's negative 54 revolutions per minute. And I should clearly say here, by the way, that our span, actually I'm not going to put it up there, give myself some room. My span for this is the throw. So span that we're applying these formulas to is the throw, beginning to end of the throw itself. Okay. What else do I know? I know that the rotation of the frisbee, I don't know how long the throw takes, but I know that the rotation of the frisbee, delta theta, angular displacement, is 1/2 a revolution. But again, it's going clockwise, so that's negative 1/2 a revolution, or negative 0.5 revolution. First thing I want to do is get all these numbers into MKS units. So I'm going to do that first with the angular velocity. I've got two conversions here. One is 1 revolution is equal to 6.28 radians, and the other is minutes into seconds. 1 minute on top, 60 seconds on the bottom, and that gets me and final angular velocity of negative 5.65 radians per second. That's my final angular velocity. The delta theta is negative 1/2 a revolution. 1 revolution is 2 pi radians, so this is negative 1 pi radian, or negative 3.1 radian. Okay, so I can then use the big ugly formula that doesn't have time in it, but that does have alpha is equal to omega squared minus omega naught squared over 2 delta theta. Arrow 0 omega squared, and I get negative omega naught. No, my bad. Ha ha ha. I get to go back when I make mistakes. Oops, went too far. Over 2 delta theta. My initial velocity is 0, initial angular velocity. So, omega, negative 54, no, doing well here. It's Friday afternoon no it's not, it's Tuesday. Shout out through the math. 5.65 radians per second, quantity squared, all divided by 2 delta theta, which is negative 3.1 radians. Let's see if we can do some math. Okay, I get negative 5.2 radians per second squared. All right, that's the angular acceleration during the throw. I actually have a feeling that my estimate of 54 RPMs is on the low side. So be it, we move on. Next, part B. The frisbee is caught 3.8 seconds later. B is in blue. And we're asked to find the average angular acceleration as it flies through the air. So, all right, in this case we have an initial angular velocity. Our new span is from the instant after throw to the catch. So this is the time that it is airborne. So now my initial angular velocity is what the final was a second ago, and that is negative 5.65 radians per second. My final angular velocity is given to me in RPMs, which is terrible, 38 RPM. This was a negative 5.65, there should be a minus sign there. Okay, negative 38 R revolutions per minute. And I convert that into radians per second the same way I did before, and that's going to give me, there's this handy 0.1047 radians per second and 1 revolution per minute. You should prove that sometime. And that gives me 38 times 0.1047, but the minus sign is negative 3.98, right around 4, negative 3.98 radians per second. And I also know the time was 3.8 seconds, so I can find the average angular acceleration by the definition, delta omega over delta t. And that's going to be final minus initial, negative 3.98 radians per second minus negative 5.65 radians per second, all divided by 3.8 seconds. And that gives me a positive 0.44 radians per second squared. And the last thing I want to know is how many times did this thing rotate while it's in the air? What's the angular displacement during that time? I'm looking for delta theta. There's a number of ways I can get this. I will use the big ugly omega naught delta t plus 1/2 alpha delta t squared, just so you can see this one be used once. Let's see, initial omega is negative 5.65 radians per second times 3.8 seconds plus 1/2. The angular acceleration is positive 0.44 radian per second squared. I make a quick note that it's positive, but the angular velocity is negative, and so it's slowing down. Its air resistance is what actually slows down the rotation of a Frisbee. And it may not slow down this much, but I've seen them slow down. I really have. Back in my day, 3.8 seconds squared. Let's do some math. And I get an answer of delta theta is negative 14.1. I'm just going to leave it as negative 14 radians, which is stupidly not very much. Yeah, and that's I screwed up the math. That's not negative 14, that's negative 18 radians. And that's the answer. That's wrong, by the way. Frisbee rotates more than that. That's only about 3 revolutions in 3.8 seconds. But that's because my estimate at the beginning of the revolutions per minute was way too low. So these numbers are off because I don't know anything about Frisbees, but that shows you how to do the problem. And so that's it. We're done. Thank you.